Another topic we need to discuss is combining functions and shifting and scaling graphs. One way that we combine functions is through algebra of functions. That's the sum, difference, product, and quotient of two different functions. Here we're given the functions f of x equals the square root of x and g of x equals the square root of 1 minus x. If we're asked to find f plus g of x, f plus g of x is given by f of x plus g of x. Since these two are not like terms, they cannot be combined together. For f minus g of x, that is just f of x minus g of x. F g of x, since there's nothing between the f and g, is understood to be multiplication. So this is the product of f and g. So that's the product of f of x, which is the square root of x, times g of x, which is the square root of 1 minus x. The quotient, f divided by g of x, is just f of x divided by g of x. Another way that we combine functions is through composite functions. This is read f of g of x, and it's f composed with g. F of g of x means just that. We take g of x and we plug it into our f function. The domain of f of g of x consists of the numbers x in the domain of g, for which g of x lies in the domain of f. We can think of composite functions this way. We take an x and we put it into our g function and we compute g of x. Then we take the g of x and we plug it into the f function, and that gives us f of g of x. Here's an example of the same two functions, f of x equals the square root of x and g of x equals x plus 1. If we're asked to find f of g of x, that means that we're actually finding f of x plus 1, since g of x is x plus 1. What that means is that we're going to go to our f function, and instead of having the square root of x, we're going to replace the x with x plus 1, which gives us the square root of x plus 1. G of f of x is g of f of x, and f of x is the square root of x. That means we're going to go to the g function. Instead of having x plus 1, we're going to replace the x with the square root of x, which gives us the square root of x plus 1. G of x means that we're going to be computing g of x plus 1. That means we're going to go to the g function, and instead of having x plus 1, we're going to replace the x there with x plus 1. Now this one can actually be simplified since we have like terms, and we would have x plus 2. Some other things we need to think about are how sums and differences in functions affect the graphs of functions. For example, if I add a constant to the end of a function, it shifts the graph either up or down. If k is positive, it shifts the graph up k units. If k is negative, it shifts the graph down the absolute value of k units. Also, if we actually add the constant to the x inside the function, it shifts the graph to the left h units, and if we subtract the h from the x, then it shifts the graph to the right, the absolute value of h units. Here's an example of adding a constant to the end of a function. In below you will see the graph of y equals x squared. Above that you will see y equals x squared plus 1 and y equals x squared plus 2. Y equals x squared plus 1 is the same graph shifted up 1 unit. Y equals x squared plus 2 is the same graph shifted up 2 units. Y equals x squared minus 2 is the same as y equals x squared shifted down 2 units. When we add or subtract a number inside the function to the x, so if instead of x squared we make it x plus 3 squared, then that shifts the graph to the left 3 units. If we subtract 2 from x, so we have x minus 2 squared, that will shift the graph to the right 2 units. This is the opposite of what a lot of people think. They expect adding to move in the positive direction and subtracting to move in the negative direction. So you need to pay close attention to that. Adding does move in the negative direction here, and subtracting does move in the positive direction. As far as scaling of graphs goes, we can stretch and compress our graph by multiplying by factors. If we multiply a function by a constant, that will stretch the graph vertically by a factor of the same constant. If we multiply a graph by 1 over a constant, or 1 over c, that will compress the graph vertically by a factor of c. If we multiply the x inside the function by a constant, that compresses the graph horizontally by a factor of c. If we multiply the x inside the function by 1 over c, that will stretch the graph horizontally by a factor of c. A couple of special cases occur when c is -1. Y equals negative f of x is the same graph as f of x reflected across the x-axis. The graph of y equals f of negative x is the same as the graph of y equals f of x reflected across the y-axis. Here are examples of vertical stretching and compressing. You'll see the graph in blue in the middle is y equals the square root of x. When the square root of x is multiplied by 3, that stretches the graph by a factor of 3. When we multiply the square root of x by 1/3, y equals 1/3 square root of x, that compresses the graph by a factor of 3. If the 3 is actually inside the function and multiplied times the x, so if we have the square root of 3x, that compresses the graph horizontally. If the x is multiplied by 1/3 and we have the square root of x over 3, or the square root of 1/3 x, that stretches the graph horizontally by a factor of 3. The two special cases we talked about, if we take y equals the square root of x, if we multiply the square root of x by -1, we have y equals negative square root of x, you'll see the pink graph, which is a reflection across the x-axis. If we multiply the x itself by -1 and have this y equals the square root of negative x, that is a reflection across the y-axis.